Okay, thank you very much. So first, I should probably share my screen.
Yes, let me make you the host.
Yes, okay.
Cool, you're the host now, so you should be able to screen share.
IntelliJ, share.
Got it.
Okay. I hope you can see the IDE.
Yeah,
That's where we will be coding today. So thank you very much for the introduction. It's great to be back at Scala at the City, this time in virtual form because of the circumstances. Next time, maybe physically, who knows. So my name is Adam Warski. I come from Warsaw, Poland. I'm currently in Mazury, Poland. So that's our lake district. It's very nice when travel will be allowed once again and safe. You should visit. It's really a nice place. So what I would like to do today is go through the implementation of the happy eyeballs algorithm using ZIO. We will look into how to implement a not so complicated concurrent algorithm using ZIO combinators. We will look at structured concurrency, what is structured concurrency, how it benefits us, and yes, hopefully what we code will actually work. So first, a short introduction on what happy eyeballs actually is. So it's an algorithm which is implemented probably in your web browsers. It's concerned with resolving host names to IP addresses and connecting to one of the IP addresses to which a host name resolves. So if you have an address, it's being translated to IP addresses by using DNS, but the DNS actually returns multiple IP addresses, right? So, and if you have multiple things, then you of course have a problem because we have to choose something, right? If you have one, it's easy, but if you have more than one, then you actually have to choose something. What does Zoom say to me here? Enjoy, okay, thanks. Okay, so we have to choose one. So this algorithm specifies one way of choosing an IP address to connect to. The algorithm is formally specified in an RFC so that it can be implemented in the browsers. We will go through quickly through the implementation here. I think it's not even simplified. So the goal is to connect to one of the IP addresses in a reasonable time and using reasonable resources. So one strategy, one obvious strategy would be to connect to the first one. It's on the left here. If this fails or times out, then to connect to the second one. If this fails or time out, connect to the third one, and so on. But it would be too slow, right? If this timeout here is long, it would cause, and if the first IP address is actually not working, this would cause poor user experience. So the lazy strategy is too slow, so we can't use it. Another strategy would be to connect to all IP addresses at once and see which one actually gets, which one connects first. So it's a kind of a greedy strategy, but this strategy is too resource intensive. It would be too costly if like a host name resolves to, let's say, 20 IP addresses. We would most of the time waste resources connecting to 20. We would waste time opening 20 sockets instead of just one. So the greedy approach is not good as well. And happy eyeballs defines a kind of a middle ground, combining the best of two worlds. So the way the algorithm works is that it first tries to connect to the first address. But if opening that socket to the first IP address takes too long, if a delay passes, then we try connecting to the second IP address. If this fails, or if the delay passes, we try to connect to the third one, right? So we try them one by one with a short delay. I think the delay by default in browsers is 250 milliseconds. So we allow these to take long, but if the first one takes too long, we try the second one after a delay, and so on and so on. So this way we get reasonable speed, so our users are happy. That's where the name comes from. Happy eyeballs. The eyeballs are the eyeballs of the users. And we don't use too much resources. So most of the time, if the first IP address is good, we will connect to the first one right away. And this was used as an example this was used as an example by Nathaniel J. Smith in his talk about his Python library Trio, which is also a library which is used to do concurrent programming, but of course in Python. And since it has been used as an example for other libraries as well, and ZIO is the latest addition to that collection. So we will try to implement that in ZIO. Before doing that, a short mandatory introduction on who I actually am and why would I be a good person to talk about concurrency and concurrency in Scala. So I've been a backend engineer for 14 years, and out of these 14 years, 8 of years doing Scala. It was actually a surprise when I wrote this to me that I've been doing Scala longer than I've been doing Java before. So I've been doing backends in J2E for a start, using JBoss technologies, then Spring, then Java, then doing concurrent backends and concurrent algorithm by hand using mutexes, semaphores, but it was a pain. And then finally doing this using various flavors of Scala. And here I am now using sometimes Monix, sometimes ZIO, sometimes Akka, depending on the use case. I'm a software engineer and the co-founder of SoftwareMill. We are a company which is doing custom software, mainly on the backend, but also end-to-end systems, including frontends. We are doing consulting, especially in the areas of Scala, Kafka, and Cassandra. I'm also involved in a couple of open source projects for Scala, like STTP, Tapir, but also I've had a Java episode at the beginning of my open source career with Hibernate Enverse. And I have a blog and Twitter, which feel invited to visit. Okay, so let's start our live coding. So we will actually go to the happy eyeballs object over here. So our goal is to implement the algorithm. So, but we'll actually implement a more generic version. So we won't be concerned with sockets and opening network connections just yet. What we will do is we will take any number of tasks, which they are, by assumption, they are some kind of uniform tasks which have different parameters, which can take a non-trivial amount of time. And we will try to implement an algorithm which runs these tasks using the delays as specified here. So that will be our first task. And after a delay, we want to run the second task. If this task fails, we want to run the third task, and so on. So a representation of a task in ZIO is the ZIO data type. So we will take a list of tasks from which we want to choose the winning one. A task in ZIO, a description of a task in ZIO is described using the ZIO data type. The task will return a value of type T, right? So we have to parameterize our algorithm with type T. It is allowed to throw arbitrary errors, and we also allow arbitrary environments. So throwable. So once again, we have a list of tasks. Each task, the first type parameter over here describes the environment, so the dependencies of the task, so what kind of services the task uses. So these are just any services. We are not constraining here. The second type parameter specifies what kind of errors the task might end in, and we say that it can be an arbitrary throwable error, so an arbitrary exception. And a result of each type algorithm applied to the two sockets, the T would be the socket over here. But in general, it doesn't have to be. And so we have this list of tasks, right? So this list corresponds to the A1, A2, A3, A4. And we want to create a bigger description of a process which runs these tasks concurrently according to that algorithm. So the result over here will also be a description of a process which uses the same environment because these tasks require the environment, but we will also use the clock dependency to schedule the delays. And we will report arbitrary errors, and we will return a value of type t. And there's a question. How can I look at the question? Why not? Okay, unfortunately, I can't look. I know why I can't look at the question. Because, okay, why not wrap the whole list in ZIO as opposed to each element? Okay, that's a good question. So a ZIO data type describes a process which can have side effects, which can run concurrently, which can take a long time to complete. So we need to have each of these processes over here. So each of these processes over here needs to be represented separately. So if we had a ZIO of a list of values, that would be a process which would compute a list of values. And we wouldn't be able to do anything useful with that. Well, at least as far as this algorithm is concerned. Instead, what we need is we need to have these processes described separately so that we can run them separately, right? We first want to run the first process, and after a delay, the second one concurrently, after a delay, the third one concurrently, and so on, until we find a successful one. So we need to have separate descriptions of these processes. That's why we have a list of processes here. And what is also important is that this description, this representation of a computation and of a process, it's lazily evaluated. So it's just a description. It's not something that's already running, which is if you have worked with futures, a future is a background computation that is already running. Here we have a description of a computation which can be run in the future on demand. So that's like a lazily computed description of a computation. And we also here return a description of a computation which can be run sometime in the future. So let's see, there are more questions. Does each ZIO task correspond to a thread being utilized? It can, but it doesn't have to. So it's a description of a process. So this process might spawn threads, or rather it might spawn fibers, which are kind of lightweight threads. We will get to fibers a bit later. So in general, it's just a description of a process. It can be, for example, a process which connects to a socket, right? We can have a process which prints to the console, which prints something to the console. So this description of a process might involve doing things in the background, starting threads. It might involve just doing some side effects. It might involve opening a network connection. We don't know. It doesn't have to correspond to a thread, but it might use threads in the background. Okay, let's go back to the presentation mode. Sorry, that's the signature of the function that we will implement. So let's start implementing our algorithm. So what we can do first here, we need one more parameter, which is the delay. The amount of time we want to wait until we start the second task. So what we can do is we can inspect the tasks list, and there are basically three possibilities. The task list can be empty. If there are no tasks to execute, we can't really do much, and it's actually probably, we'll just put it here so it's more readable. If there are no tasks, it's actually an error to use happy eyeballs without any tasks. So we will just fail the computation with an error, illegal argument exception, no tasks. If there's a single task, so the list has a single task description, well, the only thing we can do is return that task, right? There's nothing we can do about it. if there's only one IP address to which we can connect, we have to try connecting to that IP address until it actually succeeds, or timeouts or fails with other with another exception. So these are the simple cases. Now the third case is that we have a first task and we have other tasks. So this will be the list of other tasks, and we know that this list is non-empty, right? Because if it was empty, this would cover it. So we know that we have at least 2 tasks. So now what we want to do is we need to run concurrently. Concurrently, we want to run 2 things. We want to run the task process, right? And we want to run after a delay. So we want to sleep up to delay. So this ZIO.sleep creates a description of a process which sleeps for the given delay, and that doesn't do anything else. And after sleeping, so we want to sequence 2 things here, and later, let's say in English first, and later what we want to do is we want to run our algorithm using the other tasks, right? And so we want to apply to other tasks using the delay. And we want to run these 2 concurrently. And whichever finishes first should win. And we want to return the value for the branch that actually completed first. So let's implement that. First, let's take care of the and later. So here we need to sequence 2 effects, 2 processes, or 2 descriptions. The first one is the sleeping, and the second one is running our algorithm on the other tasks. So we can do it in a couple of ways. ZIO provides a handy method for sequencing 2 processes. It's a star greater. We can also use that's equivalent flat map like that. It's the same thing. It's just very common that you sequence 2 effects one after another, so that's why we have this shorthand method. So now we have 2 descriptions, 2 processes that we want to race, right? We want to run a race between them, and whichever finishes first has to return the value, right? If this socket connects first, we want to return it. If this process returns a socket first, and this process amounts to sleeping and running our algorithm for the other tasks, we want to return that socket first, right? So if we want to look at the picture, that's a race between this task over here, and after a delay, we run the same logic for this part over here. So if you want to race if you want to race 2 tasks, we have a special combinator for that in ZIO. It's called race, unsurprisingly, and it takes it takes 1 parameter. So that's the race method takes, well, it's a method on this process, and it takes 1 parameter, which is the other process with which to race, and it creates a description of a task which will run these 2 concurrently and return the value for whichever process wins first. The losing process will be interrupted so that we don't do any unnecessary work. Interrupted meaning that as soon as possible, computing that process will actually stop. So as soon as possible meaning, for example, when we encounter a flat map or some other point where ZIO can actually go in and enter and stop the computation. So we are almost done. There's one detail that we haven't covered, and that's what happens if there's an error. Well, if the task over here ends with an error, we want to run the second portion right away, right? We don't want to wait for the whole delay to pass before running the rest of the computation. So we don't really want to, we need to modify the task, and we need to say that, well, we want to race between a task, and here we want to either sleep or wait if or finish sleeping as soon as this task fails. So we need to somehow signal that this task has failed and interrupt that sleep, and if that happens, run the other portion right away. So we need to create a signaling channel that will signal that an error has occurred and that we should do something else instead of sleeping. So for a signal, we will use a single element queue, which will just hold a unit, and the unit will be the signal that an error has occurred. We'll hold at most one element. So we create that queue. That's also an effect. It's also a description of a process which creates a queue. And we will call our queue our signal task failed. So the first thing that we will do is we will create, we will modify our task, this task over here, so that it signals when there's an error. Task with signal on failed, task on error, and we say task failed.offer. So if there's an error in that task, we fill that queue with a single element. And now we create another process description, which will either sleep or finish successfully when there's an error in the task. So sleep or failed is a process description which sleeps for the given delay, or it's also races with task failed.take. Task failed.take is also a description of a process which takes an element from a queue, and that queue can be filled concurrently by another fiber in the background. So, and what we want to do here is we want to return, instead of task, we use this, and instead of sleep, we use this. Okay, and we are done. That's our implementation of a happy eyeballs algorithm. So now it would be good to see if it actually works. So let's first take a look at the print line example. So we will go to sockets a bit later. So here I have a couple of descriptions of, well, I have two descriptions of the processes. The first process that I have here will first print a message that it's starting, then it will sleep for the given duration, and then it will print a log message that it's actually done. The second type of process that we will be using will also print a message. It will sleep for the given amount of time, and then it will fail. So here we have that it fails io.fail, right? So this simulates sockets which connect after, so this will correspond to a socket which connects after the given duration, and this simulates a socket which fails after given duration. And so these methods, both of these methods create descriptions of side effecting, potentially concurrently running processes, which we will use. So let's first create our happy eyeballs process. So we apply our happy eyeballs algorithm to a list of processes. First, we will, the first task will take 10 seconds, so quite a long time. That's task 1. The second task will fail, print sleep fail. It will fail after 1 second. It will be task 2. The third task will complete after 3 seconds. The fourth task will complete after 2 seconds. Same for the fifth task. And that roughly corresponds to what's happening on the image here. You can see that this one takes a long time. So this one is shorter, so it takes like 1 second and it fails. This connects after 3 seconds, it's a bit longer, and this one after 2 seconds. And we really never get to the fifth one. And let's say we will call our happy eyeballs algorithm with a delay of 2 seconds. So let's first think what should happen, right? Well, we should start running task 1. After 2 seconds, we say that takes too long. Let's try the next task. So we try this one. And on second number 3, this one should fail. That's 2 plus 1, right? This one should fail. So on second number 3, we should start task number 3. Then after yet another 2 seconds, we say this one takes too long as well. So let's try running this one. And that one should win, and we should never see number 5. So let's assign it a result. And let's actually run it. So what we will do is result tab. We will just log the name of the task that won. And we will false, so exit code dot failure. exit code dot success. So we are using a ZIO version of an app. So that's not the Scala app, that's ZIO.app. And ZIO.app requires us to return a description of a process, which returns an exit code. So, and also all errors have to be handled. Here I'm using the fold method to specify that if there was any error, just return exit code failure. We don't log anything. And if there was, if we computed the value successfully, just return success. We'll use untrace so that we don't get stack traces. And now we can run it. Let's see if it works or not. And if it compiles, of course, the compiling in Scala is like 90% of success. Okay, and we can see that we have started the first task. So we have started the first task, right? After 2 seconds, we started the second task. After 3 seconds, the third one. But that failed. So, sorry, the second one failed on second number 3. So we started the third task, the fourth task, then the third one completed 3 seconds later, as specified over here. And it won. So the other one, the task number 5 was never started. So we have kind of proven by example that this works. That's of course not a proof, but it's as good as test as another. Most unit tests are proofs by example. So let's now try applying our algorithm to sockets, because that was our original goal. So to apply this to sockets, what we will have to do is we will have to wrap some Java blocking code. So Java contains the blocking code to resolve host names, and it contains blocking code to connect sockets. So we will have to wrap this blocking code into our nice effects. So we will use the effect blocking method from ZIO. It takes a chunk of blocking code and it creates a description of a process which actually probably manages the threads to run these blocking things. So we use the inet address from Java, get all by name. Let's use debian.org because it resolves to multiple addresses. We convert that to a list. And now we map this effect. So we take the addresses. So for here we have a list of IP addresses to which this host name resolves. So now we need to create a description of a process which connects to each of those addresses. So we take these addresses and we map them to a list of effects. So again, that's an effect blocking a new socket address 443. We open HTTPS connections, right? So just to reiterate, this returned a description of an effect which contained a list of IP addresses. And now we map this to a list of effects. So this will be like nested ZIOs. So the type of this whole thing will be a description of a process, which computes a list of processes which are not yet run. We don't do anything with them, but we will use our happy eyeballs algorithm. So we use happy eyeballs on our tasks with 250 milliseconds. And now we need to tap so that we can see which one actually won. And we will write connected get socket address. And we once again have to fold exit code failure, exit code success. And it's a method over here. And let's run it and see what happens. And then, yes, we got a connected socket. Connected. You can even see that the typo is over here. So that's actually the code that I wrote. Okay, so if you are like me, you would see that well, that's looks very nice. It's a very compact representation of our algorithm, and you know you probably want to brag about it, so you write a blog about it and you put it on the internet. But then the internet comes back to you, and there's somebody who's smart enough to spot a bug. So even though ZIO and declarative concurrency will only get you as far, there's still a problem with that code that needs to be fixed. So there are no deadlocks or anything like that. However, there's a subtle thing. So we might actually end up with multiple connected sockets. So let's actually go back to the one over here. So here we have a race between two processes. This one opens the first socket on the list, and this one opens one of the other sockets on the list, right? And it is possible, because they are running concurrently, it is possible that they end connecting a socket at the same time, right? So even though the losing side is, so an arbitrary side is being interrupted, it has already connected a socket, and we end up leaking resources. So that's not good. So we need to somehow modify our algorithm so that we close any extra sockets that we open. Luckily, we can do that in a quite an elegant way. So we can wrap our happy eyeballs algorithm in a releasable version. So let's copy the signature, it will be the same. So we will create a variant of our algorithm, also takes a list of tasks and a delay duration. It will also take extra parameter release extra. This will be a method which, for a given value that has been computed, will return a process to actually close or to release the resources associated with that value. This needs to be a process which has all errors handled, and we don't care about the return value. So these are the parameters of our method. So the way we will use it actually is the way it's intended to. So the thing that it's supposed to do is that it's supposed to call the release extra on any sockets that have been open in excess to the one that has actually won. So what we will do is we will sequence a number of effects here. We'll see what will yield. So we will create a for comprehension, which is yet another way to sequence effects. So we have seen a flat map with which we can sequence effects. We have seen the star greater method, and we can also use a for comprehension to create a sequence of effects. So first we will create a queue which will hold all successfully connected all successfully computed values or all successfully computed connected sockets. It's bounded by the number of tasks on our list, right? It's not possible that we actually successfully compute more values than that. We will then modify our tasks and queuing tasks.map. So we will create a variant of our task, and we will say that when our task exits, we want to do something. So our task, each task on that list can complete with two possible scenarios. It can either complete successfully with a value. If it completes successfully with a value, we put it on the successful list. Or it can fail. Then we don't do anything, right? Because it didn't manage to complete any value. This on exit callback, it is guaranteed to be run when the task finishes, when the task is finished computing, either by interruption or successfully. And because of that guarantee, this algorithm actually works. That's one of the reasons why it does. So for each task, we create a variant of our task, which when it exits, puts the successfully computed value on our queue. So now we have a list of tasks which enqueue. So we run our happy eyeballs algorithm with these modified tasks. Enqueuing task using the delay. Now, because we are sequencing effects, right? That's the first effect that we are sequencing. That's the second one. So when we get here, we know that happy eyeballs has completed successfully. Otherwise, we would just get an error, and the next step in the sequence wouldn't be called. So that we now know that there has to be at least one successfully computed value, right? So we can actually destructure. We can take all values from the queue. So take all is a description of a process which takes all values from our ZIO queue. And we know that there's at least one successfully computed value. So we want to return that first value, but we also, before returning, we need to release all the other ones. So what we do is we sequence yet another effect, which is a for each. So for each for each excessively computed value, we want to call release extra. And that's the description of our releasable happy eyeballs. So now we can actually go our test. We can call releasable happy eyeballs here. We need to provide an extra parameter to release the socket. So we will define a method close socket. It will be a description of a process which requires the blocking service, doesn't report any errors, and doesn't return anything useful. It will be, again, an effect blocking, which calls close on the socket and handles on all errors by ignoring them. And we are doing that on purpose this time. And we have to pass that parameter here, right? So that's the code that should be called for any sockets that have been allocated in excess. So now we can run this thing once again. Yeah, and it worked. So let's pause for a moment and think why did this actually fix our problem? So what are the crucial properties of ZIO which make this work? So the problem, the bug that we have faced is that these two processes might end up computing the value at the same time. The other one is interrupted. And the crucial property here is that even though it is interrupted, this whole process that is described here, the race process, won't finish, so it won't complete successfully until the interruption has completed successfully as well. Because of that guarantee that the whole process finishes only when one of the value is completed successfully and the other one has been interrupted and the interruption finished, because of that guarantee, we can be sure that by the time we get over here, all of these processes have either completed successfully and filled the queue with the value, or if they have been interrupted, that the interruption completed successfully so that ZIO actually got to a point where it could interrupt the process. And it got, and so the process either finished and offered and called that code over here, so it filled the queue, or the process was finished before connecting the socket. And because of that property, this actually can work. Okay, so now let's look at where are the threads and where are the fibers, where's the concurrency. So here we have the best kind of concurrency that there can be, because we don't deal with any fibers, we don't deal with any threads. It's all declarative. And if we can do that, if we don't have to mess with fibers, it's all for the better. Actually, behind the scenes, there's a couple of places where fibers are being run. So one such place is race. Race creates a description of a process which actually starts two fibers. Fibers are lightweight threads, so there can be many fibers running on a single thread. For example, we can have, like, if there's a fiber which executes the sleep process, it won't occupy the operating system thread. It will be put aside and it will be taken back into the execution queue only after the delay, and so on. So, so behind the scenes, ZIO will actually create two fibers. One will run this process, the other fiber will run this process, and they will be run concurrently. And whichever first completes will win the race. The other one will be interrupted. So that's there are fibers here, but we can't see them. And by the time this process completes, these fibers are gone. They are not running in the background anymore. So that's one place. Another place is if we take a look at the test socket, the effect blocking. This also runs this blocking code over here. we don't want to block the pool of fibers which takes care of all the main computations. So there's a dedicated thread pool on which this blocking code runs. So this will also be run on a fiber which will run on a separate blocking thread pool. And that blocking thread pool is specified by that dependency over here. This way we get to structured concurrency. Structured concurrency is a concept which was introduced by Martin Sustrick in one of his blogs, but it was later popularized by Nathaniel Smith, the same person who I mentioned at the beginning. He was giving the talk on happy eyeballs using the ZIO Python library. He wrote a blog on how the Go statement is considered harmful. How is it similar? How is it the concurrency equivalent of GoTo, and why both are harmful? So it's a very nice read if you have the time. So I recommend that. The basic idea of structured concurrency is quite simple. Once you, of course, it seems obvious once you read about it. It's not so obvious before you read about it. So the idea is that the layout of the program in its textual form should correspond to its execution flow. So it's what we are used to, like if you saw a GoTo which goes to like some completely random place in code, you would be very surprised and you would have no idea what, you would have a very hard time piecing together how this code actually works. The same with threads, right? If we just start a thread running in the background, it's like a side effect. It's doing something. We don't know when it will finish. So the idea here is that the scope in which a thread is running should correspond to its textual, to the textual form of the program. In other words, we don't want to have these thread side effects. In that if we have a method, we don't want threads to leak when these methods when the method completes. And yet, in other words, we want the fibers and the threads to be an implementation detail of the method, and not a side effect. And how does it look? How does it look in ZIO? Well, first of all, let me just minimize this. First of all, what we can do is we can use these high-level combinators, like racing two computations, like running two computations in parallel and zipping the results, or collecting all results from a list. We can have a list of processes, we can run them all concurrently and collect the results. So these are all high-level combinators which allow us to avoid using fibers directly at all. And if you can use them, great. You don't have to be concerned about fibers. That's not always possible. Then we can work with fibers directly using ZIO. So the second possibility is using the .fork method. The .fork method transforms our process description. So here we have a process, a description of a process which sleeps for 3 seconds and prints something on the console. And fork will cause it to run in the background in a fiber. So this process will actually have, it's a description of a process which has the side effect of starting a background fiber. By default, all running fibers will be interrupted when the parent fiber exits. So that's not quite structured concurrency because we don't really know where the parent fiber is started. The lifetime or the scope of this fiber started here extends beyond this method called this value, right? So that's not structured concurrency, but we can do structured concurrency if you want to. So we can manually create scopes. So here we have an example where we create a scope. So that's like a fiber. If you know the ZIO library, that corresponds to the nursery from ZIO. It's like a namespace for threads. So we create a new scope where fibers will live. That's an effect. That's a description of an effect which creates the scope. We get back the open scope, and then we specify what should actually happen inside that scope. So here we have a description of a process which prints something to the console. Then again, here we have a process which prints something to the console after a delay. but we fork it, so we run it in the background in this open scope over here, right? In the scope that we have opened over here. So we fork it inside that scope. So this fork will be this fiber will be scoped by what we have created here. We also add a callback just to see if the process is interrupted, right? So if the process completes successfully, we print success. If it completes with a failure, we will see failure. And then at the end, so that's the description of our business logic, let's say. And at the end, we add one more combinator to our description of our process, and that's we ensure that whatever happens, if it completes with an error or if it completes successfully, we always want to close the scope. So we open the scope, we pass in some process to be run inside that scope, and then we ensure that the scope is actually being closed, right? And the semantics of that is that closing the scope will interrupt any fibers that are still running, right? We haven't joined any fibers, so we could have joined. So like in this description of this business logic of this process, we can fork fibers in our scope, we can join them, so wait until they complete, and so on and so on. Here we are not doing anything like that, so let's try running that quickly. So what we should see, right, is that we have started our process. Then we have started this in the background, but we didn't allow this to complete because 3 seconds didn't pass. So this parent is done. We close the scope, which causes an interrupt to be all child fibers to be interrupted. So we have a failure of the child fiber with an interrupt, and we are outside the scope only when all child fibers have been successfully interrupted. We also can start daemon fibers, but they are like the if we want to, but they have nothing to do with structured concurrency, and but the option is there. So summing up, what we have seen is we have seen an example on how to use ZIO to describe concurrently running processes. We have seen a couple of combinators. We have seen how to implement the happy eyeballs algorithm. We talked a bit about structured concurrency, how it's best to use the high-level combinators like race, which races to processes, which creates a description of a process, which races to other processes. That way, fibers and threads become an implementation detail instead of a side effect. We have also seen that interruption is actually crucial to implement this successfully. One thing that I forgot to mention is how does ZIO integrate interruption with the blocking code. So in order not to waste time, we need to be able to quickly interrupt blocking processes, right? So if connecting a socket over here takes a long time and we have connected another socket, we want to interrupt this as fast as possible. So because we are using the effect blocking, ZIO knows that this is blocking code which can be interrupted, and it will actually use the Java thread.interrupt to interrupt this blocking code, which will throw an interrupted exception. And that way we get a nice integration between the blocking world and the non-blocking ZIO world, where interruptions are properly handled. So that's also an important part of how ZIO integrates with the Java ecosystem. And here in the interruption of this algorithm, interruption is actually crucial for things to work properly. The last thing, maybe you got a bit of a feel of that, is that programming with values is really liberating. So because we, in our implementation of the happy eyeballs algorithm, because we are operating on the level of values, so the ZIO process description over here, it's a plain value, it's just a Scala value which can be freely manipulated. It can be combined in various ways, right? It's just a description of a process. It's nothing that's already running, so we don't have to be afraid we don't have to be afraid to construct these processes. Because it's a value, we can combine it, so we can take the first value from the list and the other values on the list will be used after a delay and so on. So because we have this programming, because we program with values, we have a lot of liberty and a lot of, we can combine them very effectively. And finally, a couple of links. This presentation, if you are interested, is on GitHub, as well as the blog post, which describes this more or less what we've talked about here. The presentation about the Python library is on YouTube. We also running a Scala newsletter, Scala Times. So if you're interested about Scala news, you can subscribe. You will get a weekly digest of what's new in Scala. And the ZIO library, if you would like to use it, head to zio.dev. And I think that's all I had. So thank you very much. There's some two questions.
Thank you so much, Adam. Yeah, if you've got any questions, feel free to ask away, and we can definitely recommend the Scala Times newsletter as well. I'm a full advocate of the Scala Times newsletter, so definitely make sure you
Thank you very much.
That. Cool. So if you've got any questions, feel free to ask away. Otherwise, let's see if there's any. You've answered both of those, Adam.
Yeah, I've already answered those.
Cool.
Yeah.
Amazing.
So if you would like if you would have like any questions after the talk, just write me on Twitter or write me an email, or there's hundreds of channels right now. So feel free to do it. I'll be happy to answer those questions.
You've got one in the chat box there.
Where's the chat box? Is it different from? Okay.
Yeah, can you see the chat box? Just click the chat section down
there. Yeah, I can see it. Can you please explain race again, especially when it takes the other tasks? Okay, so the race, let's quickly go back to this one and make the code bigger. So race actually takes two process descriptions. It's a race between two processes always, well, in this invariant anyway. So, and here we have two processes which we want to compete, right? Race takes two processes, and it returns a description of a process which will wait for one of those to complete successfully. It will return that value, and the other will be interrupted. So the first process is just running the first task from the list, which signals when it's failed, but that's a detail. So that's the first task of the list. The second process contains two steps. So the first step of the second process is to sleep. The second step of the second process is to try to connect to some socket from the other tasks, right? So here we recursively run our algorithm using the shorter list. So that these are the two processes, right? Calling our algorithm using a shorter list will also yield a description of a process. That's the return type here. And we raise those two. So looking at it maybe more graphically, we raise that's the first process that we raise, and this part over here is the second process that we raise. Okay, so I hope that's more clear, not less clear.
Amazing. Perfect. Well, thank you so much.